So now that we've introduced the concept of the cross product, we're going to talk about the geometric and then the algebraic interpretation of what the cross product actually signifies. So the first thing is referred to as the right-hand rule. Now, I'm hoping that everybody has access to a right hand for the purposes of what we're doing. So these two fingers, your, let's see, index finger and, well, I was always told this one's called bad guy. These two guys are going to refer to your first vector and your second vector as you are taking a cross product. Now, if you were to orient your fingers the same way that you see the vectors opening in front of you, and I'm not talking about some weird double jointed stuff, we're talking about creating the acute or obtuse angle as defined from two vectors like these. The right-hand rule states the following: if you can orient your two fingers in the same orientation as the vectors that you see, then your thumb is going to determine the direction of the cross product of those two vectors. So when we talk about vectors in a plane, we can either have a cross product coming out of it, or we can have one going into the plane, as it were. So in this case, because I can create one where my thumb is pointing in the upward direction, this one would be u cross v points at u. Not the vector u, the person u. Whereas if we were to go to this other one, and I realized as soon as I drew those vectors that this might be a little bit more complicated, so I'm going to turn my page a little bit, just like this. I'm going to point u in this direction and v in this direction, and you'll notice at this time, well, you can't really see it very well, but my thumb would point in the downward direction. It is because of this we are allowed to conclude that that means that u cross v points away from you. So the right-hand rule is going to be a really handy way to figure out the direction in which a cross product is going to be pointed, and it actually helps to explain some physical phenomena that you've probably seen in the real world and haven't really realized that that thing is just, well, it's making use of the right-hand rule. Another way that the right-hand rule can work is rather than pointing, if you curl your fingers so that it would pass through the first vector, then the second vector, then once again the thumb dictates the direction. So over in this case, if we curve through u and then through v, you'll notice that the thumb is pointing in the downward direction. This is really kind of complicated to do with just this physical space up here, but that's okay. So that is our right-hand rule. The second geometric interpretation that we're going to give to this is going to be the magnitude of a cross product. The magnitude of a cross product works in the following fashion. There's a formula for this similar to the one that we saw for the dot product, and it goes like this. It is going to be the magnitude of u times the magnitude of v times, rather than the cosine, this will be equal to the sine of theta. Now, the way that this works is, and this one, grab a seatbelt. Pause and grab a seatbelt if you need to, because this one might be a little bit bumpy. So what we're going to do is start with the magnitude of the cross product quantity squared. Now, we have from a previous sheet what this cross product is equal to, and I have this very handy dandy sheet, and I wish that I could copy and paste this right here, but what I'm going to do is square each of these components and add them together. And I'll keep the piece of paper out of the way so that you can see what I'm writing down. So that'll be squared. The second component was u3v1 minus u1v3. That'll be squared. Then we'll have a u1v2 minus u2v1 quantity squared. Okay. Now, next up, there is some funky algebra that is about to take place. And I'm going to wave my hands at this a little bit, and I'm going to say you can totally trust me that this totally works and this is exactly the way it's supposed to be working, because I really don't feel like expanding this whole thing. So what I'm going to let you know is that if you were to expand this thing and then refactor it in a very special fashion, you would arrive at the following. u1 squared plus u2 squared plus u3 squared times v1 squared plus v2 squared plus v3 squared minus u1 v1 plus u2 v2 plus u3 v3 quantity squared. Now again, if you feel like expanding these completely and verifying that they are in fact equal to each other, you feel free to do so. Technically, a student who's taking Math 1000 should be able to do something like that without too much difficulty. Now you'll notice though that this guy right here, u1 squared plus u2 squared plus u3 squared, that's just the magnitude of u, quantity squared. You'll notice that v1 squared plus v2 squared plus v3 squared, that's just the magnitude of v, quantity squared. You'll notice that u1 v1 plus u2 v2 plus u3 v3, well, that's the dot product of u and v, quantity squared. Now the reason that this is significant is because we have a special formula for this guy right here. So this is magnitude of u squared, magnitude of v squared. And the formula that we have for this is that this is the magnitude of u times the magnitude of v times the cosine of the angle in between them. That whole thing is being squared. Now if I were to distribute the square through to all three of these factors that are in here, then both of these factors would have a magnitude of u squared and a magnitude of v squared. So what I'm going to do is factor that out. So we factor out a magnitude of u, quantity squared, and a magnitude of v, quantity squared. The first term would simply become 1. The second term would be cosine squared theta. At this point, you've probably noticed that this is a Pythagorean identity. And that Pythagorean identity is that this is equal to the sine squared of theta. Now from here, if we take the square root of this and the square root of this, we will arrive at the identity that we want. Though technically, we know this is going to be positive, we know this is going to be positive, what we don't know is whether or not the sign is going to be positive. However, when we talk about two vectors, the angle between them is always between 0 degrees and 180 degrees. That makes theta either a quadrant 1 or quadrant 2 angle according to unit circle trigonometry. Therefore, we already know that the sine of theta is guaranteed to be greater than 0. Therefore, we can arrive at our big important conclusion, which is take the square root of both sides, no need for a plus or minus sign, we'll simply get this. Now with that in mind, if I ever ask you to find the angle between two vectors, never ever 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 use this formula. This formula cannot distinguish between an obtuse angle and an acute angle. It is because of that that any time you're looking for the angle between two vectors, only use the dot product formula. This guy right back up here. Cosine can distinguish an acute angle from an obtuse angle. Now, the geometric significance of this finds its way to us in the form of area formulas. If you are given two vectors, like these two guys right here, u and v, then there is what we refer to as the parallelogram defined by u and v. Take the initial point of v, put it at the terminal point of u, and take the initial point of u and put it at the terminal point of v. This is considered the parallelogram that is defined by vectors u and v. The area of a parallelogram is the same as the area of a rectangle, which is the base times the height. You'll notice, though, in this case, that if I were interested in finding the height, I would need to do something like this. So whatever is the length of v and whatever is the length of h there. Some quick right triangle trigonometry will let you know that if you know the angle between these two vectors, that the sine of h is going to be equal to, or excuse me, sine of theta is going to be h over the length of u. Which means that if we solve for h is equal to the magnitude of u times the sine of theta. So your base is going to be the magnitude of v, and your height is going to be the magnitude of u times the sine of theta. You'll notice that that is exactly the formula that we just derived for the magnitude of a cross product. So this is a quick and simple way to figure out the area of a parallelogram if you know the two vectors that are describing it. Now, if you only know ordered triples, then that's fine. You can do a terminal minus initial thing and turn it into that. Additionally, if you have two vectors, like we did right up here, u and v, there's also the triangle defined by these two vectors by connecting the two terminal points. You'll notice that essentially what I just did is I took our parallelogram and I split it in half. It is for this reason that for the triangle defined by u and v, if you take half of the magnitude of the cross product, that will give you the area of the corresponding triangle. This one up here is the parallelogram. So that's how the cross product can be used as a shortcut to finding areas of geometric figures defined in either the Cartesian plane or in Cartesian space.